Hi and welcome to this video about hooking functions. This is the second part where we'll do something a bit more ambitious when hooking functions. If you haven't watched the first part, then I really suggest you watch that. So let's see where we are, what we need to do. So here's the code we've written in the previous video. We hooked a bunch of functions here within our local process. So now what I want to do is to extend that by hooking functions in a different process. And what I want to do here is to hook a function within Task Manager to allow us to hide processes. Could be interesting to do that. So the first thing we need to do is to create a DLL. And the reason is that the actual hooking has to happen within the target process, which means we have to place some of our code within that process. So we'll create a DLL and then we'll inject that DLL into Task Manager. So I'm going to right click this project and use a new project here to select a DLL. So I'm going to go with the desktop wizard, click next. Let's call that hook DLL very simply and use create. And here I'm going to specify that I'd like to have a DLL just to get some defaults provided by Visual Studio and a precompiled header. That's fine. We're not going to export any symbols here, even though we could, because I'm going to do something fairly simple. So let's see what we have here. The DLL is almost empty, except that it has this DLL main function, which every DLL can have. Let me just make it a bit nicer. And I'm going to change this to be called reason, just for simplicity. So we have a bunch of reasons here why DLL main is being invoked, and there are basically 4 reasons. The most important one for our purposes is DLL process attached. This is where we'd like to, in fact, install our hooks. So let's call an install hooks function, which will implement. This is where we'll install our hooks when DLL is being loaded into the target process. So let's go ahead and do that. The first thing we need to do is to get the detours DLL to be available, the detours library. Really, it's not really DLL, it's actually a static library. Let's go ahead and go to the NuGet package manager and do the same thing we did in the previous video. Just grab detours, install that in this particular project, accept licensing agreement, and we're good to go. So now we can add and include here for detours.h. So we have detours and now we need to install the hooks. So let's go ahead and create a Boolean returning function called install hooks, which will return true on success and false otherwise. If it returns false, it means something went wrong and the DLL will actually going to be unloaded. This is how the return value from DLL main is interpreted in the case of DLL process attach. By the way, for all the other cases, the return value of DLL main doesn't matter and it's not really being looked at. So we have to install hooks, and the way to do that is the same way we did that in the previous video. Let's go ahead and do that. So we have this kind of code we need to write. We have this detour transaction begin, and then we're attaching to make the actual hook and then commit the transaction. So I'm going to make sure that we're returning success here from the committing of the transaction. I can type correctly. But of course, now we have a different function to hook. And the function I'd like to hook is anti-query system information. This is a function from the native API, which is used by Task Manager and other tools to get system-wide information. In this case, we're going to focus on process-related information. So where do we get the definition for that function? Fortunately, we do get that without having to work very hard, because in the winternal.h file, there's anti-query system information. So now what we need to do is to go to that file, and there's some warnings there. I'm not going to worry about that. So we have anti-query system information. Let's just grab this function, because I do need the prototype. Kernel entry doesn't really mean anything, don't need to take that too seriously. And so I'm going to have hook anti-query system information, which is going to be our hook function. This is what we'll have to implement at the end of the day in order for us to actually be able to do something different. So there's an info class here. I'm going to just make this a bit easier to read, remove some of the stuff which is not really important, and shorten the variable names just for convenience. So we have a len here and a return length. So let me just do that. And now we can technically implement the function, which we'll do very soon. But before we do that, let's make sure we have the hook set up appropriately. So we need a declaration type for anti-query system information as before. So we have that, and we need to keep a pointer to that. That's going to be our original function. So I'm going to call that org anti-query information. This is essentially what we've done in the previous video. But in order to initialize that, I'm going to play it safe and initialize that dynamically using getProcAddress. So let's call org anti-query system information equals to getProcAddress, and we need to get the module handle for NTDLL, which is always available because NTDLL is always loaded into every user mode process. And the function name is, well, the same one, that would be anti-query system information. So we need that function and just cast it so the compiler is sort of happy. So let's do that. Here it goes. So this should be good enough. So we have this function, and then we can go ahead and make the hook. So we have org anti-query system information, and our hook function is hook anti-query system information. So with that, our hooking is complete. We're just going to hook that single function. That's good enough. Now, anti-query system information could be called multiple times for various information classes. There's a long list of information classes. The actual ones that are specified in WinTernal is a very small set, but in fact there are more than 100 of those information classes. Obviously there's 134 here, so many are just not provided by this header file. But fortunately, what we actually need is system process information, which is provided here. Even if it wasn't, we could have found that in a different way, such as looking at the process hacker header files provided for NTDLL. So let's now go ahead and make the implementation. But before we do that, the idea here is that we can hide a process and maybe even multiple processes. So for simplicity, I'm going to do that in two ways. So the first way is to hide a particular process based on its ID. So let's have a hidden process ID. And then let's have another way to hide a bunch of processes based on their names, their executable names. So let's say hidden process name. I'm going to just support one of those, not more than one. But feel free to make it more interesting by allowing more than one process to be, or process name to be hidden. This actually is a bit more challenging, so I want to keep it as simple as I possibly can without making the video too long. So I have these two global variables, but the problem is that how can we set values there? Because this is part of the task manager, is going to be the part of the process where this DLL is loaded into. So how can I set these values from outside to ask for a particular process ID and or a particular process executable name to be hidden? So we need to share this information. So I'm going to use one of the sharing techniques that I demonstrated in one of my videos. You can go back a few months and see that, by putting these variables in a shared section within the PE. So we can change that from any process that loads the DLL. So I'm going to do that as demonstrated in that video. So the first thing we need to do is to create a section by using a Pragma dataseg. You can give it any kind of name as long as it's not longer than 8 characters. And then we can add here the dataseg, the section. And then we need to provide some properties for the section. So we have the linker to tell it that this particular section should be readable, writable, and shared. That's the most important part, the S part here. So we have that, but in order for that to actually work, we have to initialize these variables. This is critical, otherwise they're going to be placed in a different section. And we also want to export them to the outside. So I'm going to add a declaration specifier with DLL export, indicating I would like these to be exported symbols from the DLL so that other processes could find or locate these variables. Now that we have that, we can implement our anti-query system information function. So let's see how that is going to work out. The first thing to do is to call the original function. We want to call the original function because we have to get the information from the kernel, whatever information that was requested here, and then if the information is related to processes in the system, then we want to intervene perhaps if we are supposed to be hiding some processes. So the first thing to do is just to very blindly kind of call the original function and have it do its thing. So we get back a status. If this fails, which means we're going to get a failure status, there's no point in continuing because it means we can't get the appropriate information. The function failed for some reason. We don't need to do anything else, just return that blindly and forget about it. If it succeeds, we want to move forward. And so for our purposes, if the information class is not system process information, then we don't care. It's some other request which we don't want to interfere with, otherwise things will be really bad for whatever process is hosting our DLL here. So let's again return the status success that we received here. Next, we need to search for our processes if the hidden PID is not 0 and the hidden process name is not empty. So if they are empty, there's no point in doing a lot of manual work. Let's just bail early. So if hidden PID is 0, that's be an indication that we don't want to hide any process by ID, and the hidden process name in index 0, that is the first character is 0, which means there's no string there, then again we don't care. There's no point in doing anything because we're not supposed to hide anything. I'm going to return the status and we're done. Now comes the fun part. Now we have to actually walk through the information returned by the system information class and then try to hide processes, because we need to hide at least one. At least that's what we're told to do. Maybe of course the process name and the process ID might not exist, and then in this case we wouldn't do nothing, but at least we have to search the list. Now I've shown how to work with anti-query system information for process enumeration in one of my earlier videos. So again, you can look at that as well. But the basic idea is that we get a pointer here, and that pointer is to system process information, kind of structure which is also provided partially by winternal.h here. And if we look at that, we can see there's a bunch of details here. Many of them are specified as reserved here. Microsoft doesn't want us to use that, but regardless, what we do need is the image name, and it is provided. So that's good enough for our purposes. We don't actually have to hunt and find the real data structure, the full data structure. So we're going to grab the information that we received here, and that's going to be pointed to this thing. And the way this works is that every process provides some information, then there's an offset indicating where the next one is. So let's go ahead and create an infinite loop here. And the way to exit the loop is if the next offset, which indicates where is the next process information located in memory, if it's 0, it means that's it. This is the end of the list of processes. That's going to be our cue to break. And of course, we're going to return the status here. So if we just do that, of course, it's not going to work out very well. We have to do something here. So the something is to check whether we have something to actually hide. So if the hidden PID is not 0, and we need to check the current process ID. If it is the same, then this is something we need to hide. So we have to do two checks here. Whether this is not 0, that is something that we need to hide, and whether that something is actually something that we are supposed to be hiding. So hidden PID equals, and in that system process information structure, there's a unique process ID, which is the normal PID of a process. But it is typed as a handle because that's the way the kernel works. But we need to just do a little casting here. This is a function or macro that casts that to a normal ulong. So if this is something we need to, that is equal, it means we need to hide that. But there is another condition. And the other condition is if we have a process name that matches. So let's check that out. We have the hidden process name. So first, let's make sure we have something here. So this is something that is not 0. If it is 0, it means there's nothing. I don't want to test anything. Otherwise, we have to do some testing. So I'm going to use the function WCS and ICMP. The testing is a bit more involved because the image name provided in the structure is a Unicode string structure and not a normal pointer to a null terminated string, which is the way the normal Windows API works. So we need to be a little bit more careful here. So I'm going to do a comparison which is case insensitive and limit number of characters I'm going to compare. So I'm going to take the first thing is the hidden process name itself, and then the current image name. So the image name is here, and the buffer member is the one that actually points to the characters, but it's not necessarily null terminated, which means we have to be careful not to compare too many characters. So I'm going to use the length here, which is provided, and divide by size of W character because it is provided in bytes rather than in characters, which is what we need here, Unicode characters. So if these conditions hold, at least one of them, it means there's something to do. We need to hide this current process. So that's perhaps a bit long-winded, but it is necessary. So we do need to do something here. Let's add another closing parenthesis. We'll see if we need to add or remove any one of those. So we have that, and now we need to actually perform the hiding. So how do we do that? We need to take the previous pointer to the process, the system process information structure, and pointing to the next one, skipping the current one, which means we need to keep track of the previous one. So I'm going to have a process information structure pointer here. Let's call that previous or prev, and make it null. So in fact, if it's not null, it means we shouldn't really be testing anything because it's probably the first process, and in this case the first process always is the idle process. We don't want to hide that ever, so we need to make sure that there is some kind of previous that we need to deal with. So that's something we need to look at here. So if the previous exists and we're testing this thing, then we have to hide the process, and this will be done by taking the previous and going to the next offset, so next entry offset, and adding that to the offset where we are at in the list right now. So we have p next entry offset, and that is basically it. However, if this is not the case, then we have to update previous to be p. So the previous is now our current process. And if previous was null initially, then we're going to set it to be this current item here, so we can hide the second process if need be. So we have some issues here perhaps with the parenthesis. Maybe we need another one for good measure. And I think that should be it. That should be it. You should probably walk through that code. You can debug that by attaching to Task Manager. Maybe I'll show that if the video doesn't become too long, and you can see what that looks like in practice. But that should be good enough. Let's build, see if this actually builds, if we don't have any kind of weird errors. So we have the orange thing here, which is not compiling for us. That's because I put it too far down. So that's one thing we need to fix. There's another thing we'll have to fix because, well, let's see. Section, of course, I have to write the name of the section. That's a good idea. And there's another last thing we might need to fix, but no, apparently this is fine because I've brought the implementation of the function dynamically. But there's in fact another thing we need to do here. We actually mess things up a little bit. So we have here the check that if p next entry offset is 0, we need to break. But obviously if we don't move p along, then we'll never get out of this loop. So we have to actually go forward by going to system process information, grabbing the current p and adding next entry offset. Otherwise we're going to be looping here forever. We have to move forward to the next process. We do need to do these kinds of castings to a pointer to a byte, so that this addition is in chunks of bytes, which is what this offset is. And otherwise if we don't make the cast, it will increment that by that value times the size of the structure, which is of course something we don't want. So that should be now good enough. So let's see if I didn't make any mistake here. Let's test it. Let's see if that works. But in fact, before we do that, we have to do a few more things. So first, we need to be able to inject this DLL into a target process. So for that purpose, I'm actually using a code that we've done already in one of the earlier examples of injecting DLL using create remote thread. This is one of the options, which is good enough for this purpose of this demonstration. So I've just copied the code basically. We can provide the process ID and the DLL path, and the injection will happen. So again, if you're not familiar with this technique, just go back and look at that example in one of my earlier videos. So now that we have that, we inject a process, DLL into a process. That's nice, but how do we make the change to these global variables that are exported outside of the DLL? For that purpose, we'll create another application which would allow us just to configure these things. We could perhaps put that in the same injection DLL executables, but that doesn't make much sense. So let's create a separate executable. Let's do a simple console application here. I'm going to call that hook config or config hook, whatever. Let's say config hook. So what are we supposed to do here? What we want to do here is to create a simple main function to accept parameters to make the changes that we want. That is to either place an executable name into that global variable where the executable name is, or a process ID, or both. So let's go ahead and do it. So the first thing we want here is to grab command line arguments. So I'm going to use wmain here because I want to get a command line that has Unicode strings. And this is important and make it just easier for me because the character array here is for Unicode characters. It makes sense because this is how these are stored with Unicode string when we are enumerating processes. So I want to make it as painless as possible. So if argc is too small, then we'll just go ahead and return a usage function here. And this usage function is going to be very simple. Just going to specify what we'd like to have here in terms of usage. That's going to be config hook. We want to have, let's say, the word hide and then a PID or a name. And if we have nothing, we'll assume that the idea is to show everything. So we'll do that. So if we have no parameters, we're going to display this little message. Otherwise, if you have a parameter, let's just make sure that it is really the string hide. So let's make sure that we have here the string hide. We're going to compare that with case insensitivity. If it is not 0, that is, it's not hide, then again, we don't understand, and we'll just go ahead and return the call to usage here. Once we have that, we know that we have one parameter extra beyond hide, or perhaps there's no other parameter. So if we have just these two parameters, I'm just going to zero out the process ID would like to hide, which essentially will show it back if it was hidden previously, and also empty the actual string. And so what we need here is to access those variables. How do we do that? So if I go ahead and copy these variables right here as global variables again, I'm going to change export to import. I would like to import them from a DLL. Now, if I just do that, let's just go ahead and try it. Let's just make the changes. So hidden PID should be 0. And I'm going to put in hidden process name at index 0, 0 as well, to indicate that there's no string there and there's nothing to do. And that's it. However, if we do have another parameter, we want to grab this parameter. So let's go ahead and assume this is a process ID. Do something like this, like a W2I with that next parameter. And we'll do something like the following. If this is 0, which also means that what we have there are actually characters and not something that can be interpreted as a number, then we're going to assume it's about a name. So we're going to copy into this hidden process name, if I can type correctly, whatever was provided in argv2, like so. Otherwise, it means the PID is not 0, which means there's a process ID there as a numeric value. Then I can go ahead and change the PID to that PID. And we're done. Now, if I try to build it, let's see what happens. So you can see that there's something weird here that says, well, you can't really do DLL import here. There's no DLL I can find here that makes any kind of sense. So what we need to do is actually load our DLL, the hook DLL, into this config process. We can do that dynamically, but in fact, it's easier to do that statically, just by loading that automatically as the process starts up. So I'm going to right-click the config hook project and add a reference to our hook DLL, like so. And this should make the compiler happy enough. Well, almost. All this initialization means nothing because we're accessing something which is not part of our process. And now it should link just fine. Okay, so we have every piece ready to go. The only thing remaining is to actually test it out. Okay, so let's go ahead and open Task Manager. So here's our trusty Task Manager. The first thing we want to do is to inject the DLL into this process. To see that it actually is happening, let's go ahead and open Process Explorer while we're at it. And I need also a command window here that has to run with admin privileges. And that's because the Task Manager is running with admin privileges and I won't be able to inject a DLL into it if if I don't have enough power, so to speak. So let me sort here by processes. Let's find Task Manager. So here's Task Manager, Task MGR. Let's see, where is it? Here goes. And when I'm looking at Task Manager, which I'm trying, we can see a list of DLLs here at the bottom, and we expect the DLL called hook DLL to appear. Right now, if you go to the H area here, we don't see that DLL anywhere, which is of course what we expect. We haven't performed any kind of hooking just yet. Now it's time to perform the actual hooking. So let's go ahead and do that and see if that works. So I need to go to where my code is. So we have, let's see, I think it is in simple hooks, something. Let's just make sure where I put that thing here. Okay, so simple hook. Okay, x64 debug, that's what I've compiled so far. So now we are ready to perform the injection, which is the first step. So let's go ahead and do that. I'm going to use inject DLL here, my little helper. As you can see, we need to provide a process ID. The process ID of Task Manager right now is 40752. And the path to our DLL is actually the same path as this one. We just need to provide the full path here. So let's just provide the full path, and the name is hook DLL.dll. So here goes. Now we should expect this to appear here around the H. And you can see hook DLL is in fact loaded into this process. And if everything went as planned, you can see hook DLL remains in the process, which means that its initialization succeeded, which means that the hook is ready to go. So now it's just a matter of testing that, see if that actually works. Okay, so I have a bunch of processes here. Let's go ahead and try that. We have config hook. With config hook, we have to provide a process ID or a name, or we could do both. So let's go ahead and start by providing a process ID. So let's go with something, doesn't really matter what. Here's some process, well, here's the Camtasia recorder I'm using to record this video. The process ID is 40236. So let's go ahead, 40236, and see what happens. And it's gone. It's just gone. Let me remove that, and it's back. Let's try with an executable. You can see I have many processes here of type code. This is the Visual Studio Code. So let me go ahead and write code.exe, see if they all go away. Well, apparently not. So apparently I have some kind of bug. There's some kind of bug here. In fact, things are really weird because it's the only one that is remaining. So we have a bug here, and that's something you might have noticed, by the way. So we can do the proper debugging, of course, but I think I I know where the bug is. So let's see where the bug is. The comparison here should really be, it's not just like that. We have to actually compare that to 0, see where that is equal. Because without that, it was actually if it is not equal. And so it actually wasn't doing the right thing. It's actually doing exactly the opposite. So that happens. Okay, so I'm going to launch a new instance of Task Manager, of course. So let's go ahead and try this again. So the first thing to do, of course, is to inject. So let's go ahead and inject our DLL. Here goes. Now the process ID is different. Let's fix that. So we have 64796. Okay, so it's in, hopefully. It shouldn't really change because that worked out previously. Now let's go ahead and see all these code processes and see if config hook here can hide all these code processes. Here goes, and they're gone. Just gone. We can also add some process ID to hide if we so desire, such as 4236 for a Camtasia recorder. That will go away as well. Once we remove that, so we show everything, code will just magically reappear. So there you have it, something that shows that we can use the same kind of hooking in a different processor. Of course, I urge you to try this out, to debug this, see how it actually works in practice, and maybe try some other ways of hooking functions, not necessarily for this kind of purpose, maybe something completely different.